Why does sand slipping through your fingers feel both dry and strangely fluid at the same time? You pick up a handful and it pours out like water, cascading in little streams, refusing to stay still. Yet each grain is a tiny rock, a solid fragment of quartz or shell. How can something made entirely of solids behave like a liquid? That paradox hides one of the most fascinating frontiers of physics, granular matter. It's a state of matter you interact with every day, but chances are you've never really thought about it. Today, we're going to unpack how sand manages to live in two worlds at once, behaving like a solid when it wants to, and flowing like a liquid when the moment is right. And once you see how it works, you'll realize that sand doesn't just explain beaches. It explains avalanches, grain silos, quicksand, and even the foundations of skyscrapers. Let's start with the illusion. At first glance, sand feels slippery because the grains slide past each other with ease. When you tilt your hand, gravity takes over, and suddenly those tiny grains stream down like a waterfall. But if you tried the same with marbles, they wouldn't flow the same way. Sand grains are so small and numerous that together they act like a continuous medium. That's why your brain interprets the sensation as liquid, even though no single grain has changed state. And yet, as soon as you try to push your hand into a bucket of sand, it resists. Suddenly, it feels heavy, dense, even immovable, like a solid wall. How can the same material be both? Here's the secret. Sand exists in what physicists call a granular phase. It's not purely solid, liquid, or gas. Instead, it flips between these behaviors depending on the forces at play. Think of it like a crowd at a concert. When everyone is standing loosely spaced, people can drift, slide past each other, maybe even dance. That's sand flowing like a liquid. But if the crowd gets packed shoulder to shoulder, movement stops. Everyone is locked in place, unable to squeeze through. That's sand behaving like a solid. The fascinating part is that this transition can happen instantly, depending on how much pressure or vibration you apply. You've probably experienced this without realizing it. Walk slowly across dry sand and your feet sink in, displacing grains like water. But try running and suddenly the sand firms up, giving you more resistance. The grains pack together under your rapid impact, locking into a temporary structure that pushes back against you. It's like the sand is deciding on the fly whether to be water or stone. This duality is what makes granular physics so tricky and so exciting. Engineers, geologists, and physicists still struggle to model it precisely because sand doesn't follow the neat equations of fluids or solids. It writes its own rules. Let's make this even clearer with a simple analogy. Imagine a jar filled with ping pong balls. If you shake the jar gently, the balls rearrange and flow. But press your hand firmly down on them and they jam together, creating resistance. Now shrink those balls 1,000 times, make them irregular in shape, and you've got sand. Each grain pushes, rubs, and interlocks with its neighbors in ways that can either free them to slide or trap them in place. That's why sand piles form steep slopes without collapsing, but also why those same slopes can suddenly give way in a landslide. Balance and instability live side by side. This is where the physics gets even more dramatic. Sand piles have what's called a critical angle of repose. It's the steepest angle a pile can hold before it collapses. For most dry sand, that's around 30 to 35 degrees. Add more grains and they'll slide down the slope until the angle stabilizes. That's why sand dunes form their iconic triangular shapes. Nature is always resetting to that magic angle. But here's the twist. Add just the right vibration, like footsteps or wind, and the whole slope can avalanche. That's granular physics in action, showing how small disturbances can tip a stable system into chaos. And this isn't just about deserts. It's the same principle engineers must consider when storing grain in silos or building on sandy soil. Understanding how sand shifts between solid and liquid states can literally save lives. Another paradox lies in how sand supports weight. If you place a heavy object like a rock gently on top of sand, it sinks in. But stamp your foot on the same surface and the grains jam, creating a solid-like platform that supports you momentarily. This phenomenon is known as force chains. Instead of distributing pressure evenly like a liquid, sand transmits force along invisible networks of grains that bear the load. Picture a spiderweb of stress lines, where some grains carry almost all the pressure while others barely feel it. These shifting force chains are why sand can sometimes seem impossibly strong and other times completely unstable. It's like trying to stand on a floor that constantly decides whether to be concrete or quicksand. Quicksand itself is a fascinating twist on this principle. It's not really a mysterious monster of nature, but a mixture of sand, water, and clay. Add water to the granular mix, and the grains lose friction against each other. The network of force chains breaks down, and the whole system starts behaving more like a thick fluid. That's why quicksand feels like it's swallowing objects. But even then, it's still granular physics, the dance of grains deciding whether to jam or flow. In fact, researchers studying quicksand have learned that struggling makes you sink deeper, while stillness allows grains to stabilize and support your weight. Once again, behavior flips depending on how the forces are applied. Now, let's scale this up. Think about skyscrapers. Many of the world's tallest buildings stand on sandy soil. How can something so shifty support structures weighing hundreds of thousands of tons? The answer is in engineering that takes granular physics seriously. Foundations are designed to spread weight widely, reducing the risk of localized collapse. Pile driving, where giant pillars are hammered deep into the ground, locks into layers of compacted sand and clay, turning a potentially unstable surface into a firm base. Without this understanding, entire cities like Dubai, literally built on sand, would be impossible. What looks like a playground material is actually the very ground on which modern civilization stands. But granular physics doesn't just help us build, it also helps us predict and prevent disasters. Landslides, avalanches, even volcanic flows all share the same underlying principles as sand between your fingers. Scientists use sand models to study how slopes fail, how pressure builds, and how tiny triggers unleash massive cascades. By pouring sand in controlled experiments, researchers can forecast the critical conditions that lead to collapse. It's one of those rare cases where a beach toy becomes a tool for survival. And the beauty of it is, the rules remain the same whether you're studying a child's sandbox or a Himalayan mountain slope. That's the universality of granular physics. Even industries rely on this hidden science. Think about how factories handle coffee beans, pills, or powders. All of them behave like sand, sometimes flowing smoothly, sometimes clogging machines. Engineers spend entire careers designing hoppers, chutes, and mixers that account for the strange dual nature of granular materials. Without this knowledge, supply chains would grind to a halt. And here's a surprising fact. The physics of sand is one of the least understood areas in classical mechanics. Unlike fluids or solids, we don't yet have a perfect equation to describe it. Each handful of grains is a reminder that the universe still has mysteries hiding in plain sight. At this point, you might be wondering why this matters for you personally. After all, it's just sand, right? But here's the eureka moment. Once you realize that sand behaves differently depending on how it's stressed, you start seeing the same principle everywhere. Traffic jams form and dissolve like grains flowing and jamming. Crowds in stadiums ripple like granular avalanches. Even how money or information flows through systems has been modeled with the same mathematics. Sand isn't just a material. It's a metaphor for complexity, showing us how individual parts can create surprising behavior when combined. That's the hidden beauty you feel when it slips through your fingers. It's not just dry grains. It's physics whispering secrets about the rules that govern both nature and society. And remember, the next time you let sand pour out of your hand at the beach, you're holding a paradox. A solid that flows, a liquid that resists, a mystery that's also the foundation of our tallest buildings and our deepest disasters. It's proof that even the most ordinary experiences, the grit beneath your toes, the dunes on the horizon, are actually invitations to wonder. Science is not hidden in faraway galaxies. It's right there in a handful of sand, waiting to be noticed. But let's take the mystery of sand even deeper. One of the strangest properties of granular matter is that it remembers. Pour sand into a pile and it keeps a record of how it was poured. If you tilt the pile later, the way it collapses will depend not only on its shape, but on the hidden history of its layers. This is called memory in granular systems. It means that every avalanche is not random. It's shaped by the invisible past of how grains settled, pressed, and locked against each other. In other words, every handful of sand carries a silent history of motion. This is why predicting landslides is so difficult. Scientists must not only measure current slopes, but also reconstruct how the grains got there in the first place. The pile remembers, even if we can't see it. And that memory has real-world consequences. Consider earthquakes. When buildings stand on sandy soil, seismic waves shake the grains. Suddenly, the solid ground beneath turns into something closer to a liquid, a phenomenon called liquefaction. Entire structures can tilt, sink, or collapse, not because the sand disappeared, but because the grains lost their ability to jam and bear loads. This has happened in cities around the world during earthquakes. Understanding granular physics is not just an intellectual puzzle. It's the difference between stability and disaster. The fact that sand can flip from solid-like to liquid-like in seconds is a reminder of how fragile the ground beneath us can be. Now let's add another surprising layer. Sand is not uniform. A beach grain is shaped differently from desert sand, and volcanic sand behaves differently again. Round grains roll easily, making dunes shift and migrate like waves frozen in slow motion. Angular grains interlock more, creating firmer, more resistant structures. This is why concrete uses crushed sand instead of rounded beach sand. The shape of each grain determines how the whole behaves. It's like a crowd where some people lock arms while others just brush past. The collective behavior is shaped by the tiniest details. That's granular physics teaching us a profound truth. The macro is built from the micro, and the shape of the smallest part controls the fate of the largest structure. Even in art and play, sand reveals its duality. Think about sandcastles. Wet sand sticks because a thin film of water creates surface tension between grains, pulling them together. Suddenly, you can build towers and arches, but add too much water and it collapses into sludge. The balance between dry flow and wet cohesion is delicate, and kids at the beach instinctively learn to tune it. That moment when you realize the perfect water-to-sand ratio is actually you doing physics with your hands. Sandcastles are laboratories in disguise, where children experiment with cohesion, friction, and stability without even knowing the terms. What feels like play is really science written in grains. Now here's the big eureka moment. Sand isn't just a material. It's a fourth state of matter in its own right, sitting awkwardly between the categories we teach in school. We usually talk about solid, liquid, and gas, but granular matter doesn't fully fit any of them. It creates its own world of rules, where friction, jamming, avalanches, and force chains replace the neat equations of fluid dynamics or solid mechanics. And once you grasp that, you realize how much of the world is made of sand-like systems. Coffee beans, sugar, rice, snow, even planetary rings around Saturn all follow the same granular laws. Suddenly, the universe looks less like neat categories and more like a spectrum of behaviors. Sand is just the doorway. Think about the rings of Saturn for a moment. To your eyes, they look like smooth, glowing disks. But in reality, they are made of billions of icy particles, each following granular physics. They jam, collide, flow, and spread just like sand in your hand. The same physics that governs your beach vacation also governs the architecture of a planet's rings. And in deserts on Earth, dunes march across the landscape in waves pushed by the wind, each one a giant expression of granular dynamics. The physics of sand is a universal script, repeated at every scale from handfuls to planets. And this is what makes granular physics one of the last great frontiers. Fluids and solids have elegant equations that predict their behavior. But sand? Sand defies simplicity. Researchers still struggle to unify its dual nature into one clean model. That's why experiments with sand avalanches appear in labs everywhere, using colored grains, slow-motion cameras, and careful measurements. Each tiny collapse is a step closer to unlocking rules that could explain not just dunes and silos, but also traffic jams, crowd flows, and even data networks. Once you see sand as a metaphor, it becomes a key to complexity itself. So the next time sand slips between your fingers, remember that you are holding one of nature's most important riddles. Those dry, slippery grains are solid stones, yet they flow like rivers. They jam like concrete, yet they collapse like waves. They build dunes that walk across deserts and avalanches that roar down mountains. They support skyscrapers and sink ships. They confuse equations but teach intuition. Sand is not just dirt. It's a living puzzle, a frontier of physics you can scoop up and pour back down. And that's the beauty of science. It shows you that even the most ordinary, overlooked details, the grit beneath your toes, are miracles of hidden order. What feels like play at the beach is actually a laboratory for the laws of the universe. What seems like a nuisance in your shoe is a reminder that matter doesn't just fit into neat categories. It adapts, balances, and surprises. And when you recognize that, the world transforms. Every grain becomes a clue. Every handful is a window into complexity. Every slip through your fingers is a lesson in how nature resists being simple. And if you want more of these keys to unlock the hidden designs of the everyday world, share this wonder with someone who needs a spark of curiosity and subscribe to how it actually works. Because every grain of sand is more than it looks. It's physics in disguise waiting for you to notice.